The objective of this lab was to find a model to fit a fast-falling object and a slow-falling object using the momentum principle, gravity, and drag. For my objects, I chose a teddy bear for my fast-falling object and a post-it note for my slow-falling object. I found the mass of my post-it note to be 0.34 grams by taking the mass I found online of an entire pack and dividing it by the number of sheets. I found the mass of the teddy bear to be 104 grams using a balance. The length of my teddy bear was 11 inches or 0.279 meters, and the length of my post-it note was 3 inches or 0.0762 meters. I used both these measures for my calibration stick. I orientated my axis so that both objects were falling in the negative y direction. I placed the origin on the floor so that the final positions would be around 0. As you can see, my bear dropped from 2.139 meters to 0.012 meters in 0.667 seconds. For this reason, I chose a somewhat small delta t of 0.005 so that I can assume that the velocity was constant for each time step. My post-it dropped from 1.69 meters to negative 0.024 meters in 2.27 seconds, which allowed me to use a slightly larger value of 0.01 for my delta t. I chose the point mass to be the bear's stomach in the middle of the post-it note to track it easily. First, let's examine my results when I created models using only the force of gravity. For my fast-falling object, I inputted my initial conditions, making sure to plug my initial velocity at 0. I used the momentum principle, the velocity update formula, and the position update formula to create my model. I included the force of drag in my equations, but kept the b 0 so it wouldn't affect my results. Comparing the data I observed from Tracker to my computer model, I found that the model was a pretty good fit for my fast-falling object. I used the same model for my slow-falling object, changing only the initial conditions, delta t, and the total time. As you can see from the graph, a model using only the force of gravity was a bad fit for my slow-falling object. The model falls way faster than what I observed. After some messing around with b values, I found that a very small b value of 0.0005 made my observed data and computer model match up pretty well for my fast-falling object. My slow-falling object took more tries, but eventually I found out that a b value of 0.0043 worked well with my observed data. The red line on the graph shows one of my earlier attempts that had too much drag. The X line beside it is a much better model. Terminal velocity occurs when the force of gravity equals the drag force, making the net force 0. This makes the velocity of the ball constant once it hits this terminal velocity. It can't go any faster. My fast-falling object didn't hit terminal velocity during its fall because of such a small drag force. You can tell this because its graph motion is completely parabolic. My slow-falling object, however, reached terminal velocity, as you can tell by its linear graph. I calculated this terminal velocity to be negative 0.881 meters per second. What if the slow-falling object had an initial downward velocity? As you can see in the model that did not account for drag, this made the object fall faster than the object that started from rest, causing it to reach faster speeds in the time frame given. When I compared the models that did account for drag, however, I found that they still both reached the same terminal velocity of negative 0.881 meters per second. This is because no matter what the initial velocity is, because b is the same for both models, and the force of gravity is too, they will reach the same terminal velocity. I did my calculations for terminal velocity by finding multiple points near the end of the object's path and checking the instantaneous velocities. I found that not only were multiple instantaneous velocities were constant for my at-rest model, but they were also the same for my model with an initial velocity of -1 in the y direction.